Modeling issues. So let us now explore several modeling issues in our simple linear regression model. We will look at two aspects. One is the effect of scaling the data. If we scale up or scale down a particular variables, what will happen to our regression? And then we will talk about the functional forms. So far we've been looking at simple linear regression model. Simple because we only have one explanatory variables. It's linear because y is a linear function of x. And you should be wondering, this linear regression, linear model may be too restrictive. Is it a case? We will look at that. Okay, let's look at the food expenditure models. We're going to use FOODEX_EXP, these variables, to denote weekly food expenditure by household of size 3. And note that the unit of this variable, this is actually y. Okay, the unit of this variable is dollar. Then using income INCOME to represent weekly household income, which is actually our x. And also note that the unit is $100. It's not dollar. It's $100. And we import the data, run the OLS regressions, we get a result. So 83.41, this is estimate upon estimate of beta 1, this is B1, plus 10.21, which is B2 estimate upon estimate of beta 2 times income. And the figure in the brackets are the standard error, the estimate of standard deviations. Note the unit of income is $100, which means if the household weekly income is $2,000, then the value of variable income is 20, right? $2,000 divided by 100, we get 20. And upon estimate of beta 2 is 10.21. This means what? This means income increases by 1 unit. Here 1 unit is $100. Food expenditure will increase by $10.21. Okay, that's how we can interpret beta 2 upon estimate of. That's how we can interpret B2 the upon estimate of beta 2. Now, if instead we scale the unit of income to be dollar rather than $100, what will happen? We can do this. We run the estimation, we run the regression, and here is the new regression results. And you should know that B2 here, previously B2 is 10.21. Now it becomes 0.1021. Remember, we scale the income by divided the income by or times the income by 100. Okay. And standard error is smaller by the same factor as well. So the estimated coefficient of income is now smaller by a factor of 100. Standard error becomes smaller by the same factor of 100. Because both the coefficient and the standard error are smaller by the same factor of 100, the t stacked and all other results unchanged, like r squared is still 0.385. Everything else is not changes. Okay, so now you can see the effect of rescaling the explanatory variables. So changing the scale of x, the explanatory variables, the coefficient of x must be multiplied by the same factor, the scaling factor. So when the scale of x is altered, the only other changes other than this coefficient change, the only other change is the standard error of the regression coefficients, of the corresponding coefficients. But it changed by the same multiplicative factors. So the ratio t-stat is unaffected, and all the other regression statistics are also unchanged, like R-squared. Okay, foot underscore exp is the dependent variables. We know that units dollar. Okay, now let's say this scale the unit, change the unit to $100 rather than dollars. What will happen? Let's do this and rescale it. So now this is the new regression result, and you should see that both B1 and B2, they're different. They are smaller by a factor of 100, and similarly for the standard errors, R-squared is unchanged. So the estimated coefficients of income and the constant intercept are now smaller by a factor of 100. Standard error becomes smaller by the same factor. So this leaves the t-stat and all other results unchanged, including R-squares. So changing the scale of y, the dependent variables. If we change the units of measurements of y, but not x, then all the coefficients must change by the same factors in order for the equation to remain valid. And now, because the error terms is scales, the least square residuals will also be squares. This will affect the standard error. Remember, standard error is computed from the one part of the formula is the residuals, which we use to estimate the sigma square. But it will not affect the ratio of these coefficients estimate over the standard error t-stat or R-squares. Okay, sometimes we can change the scales of both x and y at the same time by the same factors. Now there will be no change in the reported regression results for B2, but the estimated intercept and residuals will change. Then t-stat R-squared will not change, but the interpretation of the parameters, you need to match this interpretation relative to the new units of measurements. Okay. Right. So let's the effects we see when we rescales change the units of our x and y. So far, we have only explored a simple linear models. So these simple linear models, and we know that beta 2 measures the marginal effect of x on y. This is dy over dx, and actually I'm using curly d. Okay, so at the moment this is the same as dy over dx. Okay, so beta 2 is the dy, the marginal effect of x on y, dy over dx. And you should know that this beta 2 does not depend on x, where what value of x is. So it's a kind of linear. The marginal effect, sorry, the model is linear, so the marginal effect is constant. However, the marginal effect of x on y might not be linear. For example, let's look at this. So vertical axis is y, horizontal is x, and this blue curve is capture the functional relationship between x and y. So y as function of x. So if x takes value of x1, then corresponding y is y1. And then here there's a slope. We can find a slope. This is actually dy over dx. So this marginal effect measures the slope of this curve. Okay. So and here we see that it's upward sloping. Okay, let's move. If x increase from x1 to x2, so we move from this point to this point. And now the corresponding y2 is this level. And we can draw a slope which is tangent line, which is a line less tangent with the curve at that particular point. Tangent means touching at only one point. Okay, and we can see that now this slope is flatter compared with this. This is steep, this is flat. So we see that the marginal effect of x on y is no longer constant. It depends on what the value of x is. Okay. Then the questions: can our linear model captures this nonlinearity? Remarkably, we can transform x or y or both so that we can actually capture such a nonlinear relationship in our linear regression model, regression framework. For example, suppose that we know that y is a quadratic function of x. So then our model will be yi is equal to beta 1 plus beta 2 times xi squared here, plus the error terms ei. So now yi is no longer a linear function of xi, but yi is a linear function of xi squared. So we can think that xi squared is a new variable, new exponential variables. Okay. So now I hope you see that the linear model is not as restrictive as you may think. Okay. We can capture this nonlinearity in our linear framework. Okay, by transforming x, y, or both. So the most common transformation of x or y is power, taking power function. If x is a variable, then x raised to the power p is p power transformation. For example, like quadratic, p is equal to, so we have x squared in it. Or it's cubic, p is equal to 3, x to the power 3. Okay, that's power functions. Or this is actually polynomial. Okay, polynomial function of x. We can also do natural logarithm transformations. So if x is a variable, then its natural logarithm, log x. We can take a log at x. For example, we might have log models. Log yi is equal to beta 1 plus beta 2 log xi plus error terms. Or log linear model. Log yi is equal to beta 1 plus beta 2 xi plus error terms. Or linear log models. Yi is beta 1 plus beta 2 log xi plus error terms. Right, in terms of graph, this is a quadratic equation, cubic. So cubic, say if beta 2 is positive, it's like this. Initially increase, but at decreasing speed, which marginal effect is decreasing. Then eventually increase at increasing speed, and the dotted the dashed curve is the when beta 2 is negative. This is log model. This when beta 2 is bigger than 1, between 0 and 1, or is less than 1, equal to 1. And log linear log models. So hopefully this give you intuitive understanding of how this function looks like. Okay, we are usually interested in the marginal effect of x on y and the corresponding elasticity. So marginal effect of x on y, let's say x is our income, household income, y is food consumption expenditure. Then the marginal effect of x on y is if x changed by say $1 or $100, how many dollars will y change? And bear in mind that we have unit. When we are saying this, we have unit rate. $1, how many dollars? $100, how many dollars? So we denote this as dy over dx, and this marginal effect we now know that it's a slope of the function. Okay. Elasticity. It measures if x change, say income, household weekly income changed by rather than by $1 is by 1%. How many percent will y, the food consumption expenditure, change? Percent is not in terms of dollar, in terms of percent. So it's change of y over y. So this we get a percentage change of y. So by dividing change of y, which could be $10, by the initial value of y, $100, so we get 10% change. So we get rid of the dot unit. Then over divided by change of x over x. Okay, so now this elasticity, you should know that this elasticity is unit free. So unit free is the feature of unit free is nice, right? We don't need to worry about what units we are using, and it might be easier to compare across different regressions, let's say. Okay, so we have different functional forms here. So what is the slope? What is the elasticity? This table summarized the slope and elasticities. Okay, I'm gonna go through some of these functional forms and leave you to practice to try to work out the other functional forms. And if you have any questions, you can send me emails. We can go through it together. So let's start with the linear function. So dy I over dxi is just beta 2. So slope is beta 2. Elasticity would be dy over y divided dx over x, so which is dy over dx times x over y. Okay, so this is equal to beta 2 times x over y. So we can think that if you are not too familiar with algebra, you can think this way. Say I'm going to multiply both top and bottom by x, and I'm multiplying both the numerator and denominator by the same quantity, so that it doesn't change the ratios. So this cancels this. Then multiply both top and down by y. This cancel with this. So then I get dy times x, dx times y, and this is the same as dy over dx times x over y. That's what we have here. That's the elasticity. So let's look at log models. So d log yi over d log xi is equal to dy minus yi over dxi minus xi, and y from here to here is because of the logarithm functions. You can check with the logarithm functions, and we derive this that dy over dxi times xi over yi, and this d log I over d log yi over d log xi, which is equal to beta 2, right? So now log y is a linear function of log xi, so this is equal to beta 2. So this is the elasticity beta 2. And marginal effect, we want to only compute dy over dxi, right? So let's multiply both sides by yi over xi. xi, that cancel out. So dy over dxi is just beta 2 times yi over xi. Okay. Let's look at this reciprocal models. Okay, dy over dxi, which is beta 2. So now you need to use chain rules to do the differentiation. And this is you need knowledge of calculus. If you don't have this, that's fine. Take this as kind of formula. Okay. Minus 1 over 1 xi squared. So it's negative beta 2 times 1 over xi squared. It's this. Okay, and then elasticity is dy dxi times xi over yi, so which is minus beta 2 times 1 over xi squared times xi over yi. So we have xi on the top, xi squared on the bottom. We can cancel out 1. So it's negative beta 2 times 1 over xi times yi. So that's the elasticity. Okay, so this table summarizes the different functional forms, the marginal effect, the corresponding elasticity formula. Now we have a few functional forms. How can we choose an appropriate one? So in choosing a functional forms, we check signs consistency. So our economic theories might suggest that, okay, the beta 2, the signs should be positive. And if we use a particular functional form, say log linear functional form, we end up in finding negative signs. Then this might be because of this log linear functional form is wrong one. We're choosing a wrong functional form. Okay, so we check with sign consistency whether it is consistent with economic theories, our expectations, intuitions. And we can also check the significance of the estimated coefficients. Okay, if in a particularly, if our series, economic theory says that beta 2 should be significant, but we end up in finding a not a significant one, and that might be because we are using a wrong functional forms. And we can also check diagnostic residual plot to do some testing there. We run a regression, predict residuals, then check residuals, and test the normality of residuals, whether the residuals is normally distributed or not. And we can also formally conduct model-specific tests like Ramsey test, or heuristically we can check R-squares. Though you want to be aware that R-squares, you shouldn't choose the functional forms solely based on R-squares. Okay. So evidence of specification errors can reveal themselves in an analysis of the least square residuals. So we finish the regression, we predict residual, we can check them. So looking for are there evidence of violations of the underlying assumptions, for example, homoscedasticity. So this is a particular case for cross-sectional data where we may have what is called heteroscedasticity issues. We will address this later on. Or we want to check, besides, we want to check whether there's no serial correlations. Okay, so this may be an issue when we are using time series data. Okay, and we can test for normalities. Okay, to test normality, there are quite a few tests for normality tests for residuals. The one we can use is Jackie Beta test for normalities. It is valid in large samples, so we need the sample size to be large, and it's based on two measures. First is skewness, which captures how symmetric the residuals are around zero. And if skewness is zero, then it's perfectly symmetric residual. So if our residuals are normally distributed, then the skewness will be zero. Second measure is kurtosis. It captures the pickedness of distribution. And again, if it's normal distribution, then kurtosis will be 3. So the null hypothesis is that, okay, skewness is 0. Kurtosis is 3. So the null hypothesis is that the distribution is normal distributions. And the Jackie Beta statistics is this. It can be shown that it follows a chi-square distribution with degree of freedom 2 under the null hypothesis. And from the data, we can compute this Jackie Beta, and it will be easy to implement in R as well. And we can reject the null hypothesis at the 5% level of significance if the p-value is less than 0.05. All right, let's have a look at one more look at our food expenditure models. So now we can estimate, rather than linear models, we can estimate linear log models. So dependent variable is food expenditure. Okay, so there's table here. So this should be FOOD underscore EXP beta 1 plus beta 2 log income rather than income plus L10. And this is the regression result. You can see that we did the point estimate of B1 and B2 are quite different. and R squared change a little bit. So you previously linear is 0.38 something. Okay, so now we get 0.3565. So it changed, but changed by very small amount. So you shouldn't use this R square in choosing which functional form you want to use.